Hello, YouTubers! Hey, subscribers! How's it going, guys? Winkit, it's so nice to have you there. Winkit, I've got a question for you. Depends if you're actually there or not. I've been having problems with my microphone, and I think you're obviously well aware of that. How's the sound? I've been having problems with my mic. It's a bit echoey, but it's manageable, I think. Let's see if I can try and do anything about this. I don't know whether or not I can make it any better, what I can do to improve it. Show advanced settings, audio, automatically adjust mic volume, stereo, audio, echo cancellation is on. Okay, well, I'll stick with it this way. Right, guys, so this is the iGCSE edexcel paper 1, part 2. So I did this webinar because I had one of my subscribers, Mita, asked me to do this paper for her. So I'm just gonna continue it. I don't wanna waste anyone's time. So I'll switch over to sharing my screen. It shouldn't take me very long. I think we're over halfway through, but I think everyone is aware. Let's go to clip text, so I'm there. It'll be interesting to see how long the second half of the paper takes. So in the first half of the paper, I believe I got down to question 7. So if I go to exam review webinars, this was my paper 1. I managed to get down to question 6, and it was 1 hour and 7 minutes long to do the first one. So since I'm using my laptop microphone, I'm not quite so worried about the blurry sound anymore. Winkit, if you're there, if you hear my microphone go all crackly, please let me know. It shouldn't do based on the fact that I'm using my laptop's one. But so this paper was out of 10 in total, and I went all the way down to question number 6, and it took 1 hour and 7 minutes. It'll be very interesting to see the length of time it takes us to do the second half of the paper. The total number of questions is 10, so we'll see how we get on. So as we move through this, one of the things I should have been pointing out is the different topics that the questions are working in. So this one's in the periodic table and probably atom structure as well. In the periodic table, the vertical columns of elements are called groups. The horizontal ones, of course, we know are called periods. And it gives us a variety of elements. And oh, notice they're all group 8. So these guys are all of our noble gases. And notice that it's increasing in boiling point. So state the relationship between the relative atomic mass and the boiling point of these elements. Fine. So we will say try and zoom in as best I can, as relative atomic mass, RAM. Would I do that in a real exam? No, I'd actually quote that one. They've done it, so I'm allowed. As AR increases, the boiling point increases. Now they've deliberately the boiling point increases. They have deliberately chosen these elements because the numbers are all negative, which just makes it a little bit more difficult for students to understand what the trend is. They're checking to see that you understand that minus 269 for helium is way lower than minus 153. So it is increasing. This here is increasing, and so is the AR. That is also increasing. I always say to students, they've given us data. So it would be quite nice, if this was 2 marks, I'd want to use the data as well. So I'm just going to put helium 4, boiling point, helium 4 minus 269, lower than krypton 84 minus 153. It's just quite nice to do that and actually give data. State why the elements in group 0 are unreactive. All elements in group 0. Notice they've chosen group 0 and not group 8. Yeah, it's interesting that they've done that as well. All elements in group 0 have full outer energy levels. Now there's more detail here. Hi Meter, it's nice to see you. Oh, sorry, lagged sound is good. I'm good, thanks Meter. It's lovely to see you. Thanks for coming along. This question is a really nice question. Can I just point out, I always say there's more detail here. All elements of group 0 have a full outer energy level. Most students will end there, but I would then always add to this your understanding of what it means to be reactive, which is the gaining and losing of electrons, and these guys will do nothing. So I will put outer energy levels, outer energy level, not levels, although they probably wouldn't mind, has all elements in group 0 have full outer energy level, so don't want to gain or lose electrons. That, can I just point out, that sentence there is far, far, far better chemistry than just stating full outer energy levels. Do try to avoid the word shell. There are still lots of teachers who teach it. I still do it myself, but I always say to the students, if you write down the word shell, you should always put in brackets immediately energy level. Dead important. Okay, the elements in group 7 of the periodic table are called halogens. State why the halogens have similar chemical properties. Refer to electronic configurations in your answer. Okay, so all elements in group 7 have 7 electrons in their outer energy level. And look what I'm now going to do. I'm now going to add on this sentence here in the halogen setting. So I'm going to say, so all want to gain 1 electron. So similar reactivity. I like it. The reactivity, of course, decreases down group 7, but that's absolutely fine. Can I just say, I would not want, it's going to be interesting to mark these questions. I would not want, I don't really care about that one, but I would never do these 2 answers without those yellow bits. I would always want to add that I understand that even though they've got 7 in it, which is probably enough for the mark, I'm wanting to say what I understand that means they're going to be doing in terms of losing and gaining. I think there's far more value in that. Okay, the order of reactivity of the halogens can be shown by using displacement reactions. When chlorine is added to sodium bromide solution, the chlorine displaces the bromine. Write a chemical equation for this example. Okay, when chlorine, we know any element that ends in -ene or -gen will be in a pair. Yeah, bear that in mind. Any elements in ending in -gen or -ene will be diatomic. So we've got chlorine is being added to sodium bromide. NaBr. I hope everyone in this room is okay with. Doing the formula of NaBr. Yeah, if you're wondering about chemical formulae, sodium, of course, is in group 1 of the periodic table, so it's going to be a +1. Bromine, of course, is going to be -1 because it's in group 7. I'm just going to show that in the class anyway. I think there's some value in this. So we've got. I'll wait for my pen to appear, then make it smaller and go to red. Yeah, so we've got +1 for all of these guys, +2 for all of these guys. Variable transition metals. Key ones to remember being iron 2 and iron 3, and iron 3+. And then we've got +3 here. Yeah, +3. Then we have, doesn't really do it. They're +4 or -4, but actually they don't really do it. They're dropping into covalent at this point. Then we have -3, -2, -1, and they don't do it. So what we're doing is we picked up bromide in -1 and sodium in group 1, crossing down, and we're going to get those charges are going to cancel, so we get NaBr. You can do the little cross and down trick. I'm not a big fan of the cross and down trick, but you can do it in this case if you wish. Right, so what's going to happen is the chlorine is going to displace it, so I'm going to form NaCl. Notice the 2 is not there. That is not the case. You know that the formula for salt is NaCl, and we're going to get Br2 appearing now as a pair. And now, of course, you have to balance. Yeah, And the observation is going to be, because chlorine gas is a green gas going into a colorless solution of sodium bromide, then it forms a colorless solution of sodium chloride, but then the whole thing goes orange because you're producing bromine water. Yeah, the bromine will be dissolved in water, it'll come out aqueous. Those observations are really important. State the color of the solution formed in this, and it's going to become orange. I like it, an orange solution. Can I just point out that bromine water at various concentrations, if it's at low concentration, it'll appear yellow. But you learn for the chemical test for alkenes, you learn that the bromine water is orange to colorless. So let's stick with orange at this particular case. Explain whether or not a reaction takes place when bromine water is added to sodium chloride. The answer, of course, is no. No reaction will take place. No reaction will take place. Why? The reason why is because, I mean, if it was, that reaction up there would be reversible. The reason being is, so I'm just going to do a little bit more understanding of this particular topic. Group 7 is a tricky one, and it evolves as you move into A level. But just to actually explain what's happening, if you actually look at this from a diagram perspective, so when you have sodium bromide aqueous, that's as a solid, it would be a white crystalline solid, yeah? And when you add it into water, it breaks, it dissolves, and it forms its ions. Now, at this point, I'm going to zoom in on the bromide ion, because what does the bromide ion look like? The bromide ion looks like this. It owns sodium's outermost electron. It's taken it from it. And sodium, of course, is missing it entirely. Now, if you then bubble in chlorine gas, chlorine, of course, is going in as a pair. Now, what's actually happening in this case is that the chlorine is stealing that electron. So the actual equation that's occurring for chlorine with sodium bromide is actually this guy. You're actually forming, it's not, the sodium doesn't actually do anything. This is called the ionic equation for the reaction, ionic equation. Just showing the fact that the sodium isn't doing anything. And the reason for this is because the chlorine is more reactive. It wants the electron more than the bromine does. Yeah, it wants it because it wants it more because it's only got 3 shells. Whereas bromide, of course, is massive now at this point because it's gained an electron, so it gets bigger, and it has 4 shells. So it's the outermost electron is further from the nucleus. So chlorine wants it more. So the chlorine's just going to take it. That's just going to get swapped over. Yeah. So in terms of the other way round, it just wouldn't happen. So in the straightforward answer, of course, is no reaction will take place since bromine is less reactive than chlorine. Notice I'm not using chloride anywhere. I'm just going to add in a third sentence. So bromine cannot remove electron from chloride ion. It's nice to give that little bit of understanding as to what's going on here. Yeah. Okay, next one, the displacement reaction between, that one's going to be interesting to mark. I'm curious to see what they want from that. The displacement reaction between potassium iodide and chlorine can be represented by the ionic equation. Oh, isn't that lovely? So we were doing ionic equations over here, and now they've dropped us into it. Explain why this reaction is described as a redox. So we know that redox stands for reduction and oxidation. You notice I've separated them slightly. Yeah, and we immediately drop into oil rig. Yeah, I love oil rig. I won't actually put it on the lines. It's a waste of space. But I love oil rig. It's one of the most important things I ever got taught in chemistry. So oxidation is the loss of electrons, and reduction is the gain of electrons. Right, so if you look at the equation, what you notice is that the iodide, which has an extra electron, is turning into iodine. So therefore, it's going from negative to 0. That means it's losing an electron. So the first thing we're going to say is here, bullet point 1, iodide, I'm going to put brackets I minus, is is becoming iodine. And in this case, becoming iodine and losing, I'm just going to remove that there. Go away, little laptop. Come on. There you go. And losing electrons. This is, so which one's losing? That's oxidation. This is oxidation. Let's do the half equation for it. It's always nice to do those. So I'm going to do the half equation. So I've got iodide going to iodine. This is called a simple half equation. I've just done these with my year 12s. So the first thing we do when we're doing half equations at GCSE, the steps to solve, the methods to complete this are balance for atoms. Step 1, balance atoms. Step 2, balance charge. That's all you really do for simple. And the charge is with electrons. So the first thing I do is balance for the atoms. Let's do that in green. So 2 iodines here, only 1 iodide there. Balance it, add a 2. Right, now I've balanced for the atoms. I now need to balance for charge. To balance for charge, I need to look at the charge on either side. Now over here, I have 2 minuses. Yeah, that's exactly what it says. I've got 2 minuses. So, and on this side, there is no charge anywhere. So that's 0. So I need to balance this with electrons. And to do that, I'm going to add 2 electrons onto that side to bring it down. Yeah, there you go. That's now -2 as well. So you can see that those electrons are being lost. So there's it being oxidation. Next, let's do the next one. So what's happening to chlorine? So chlorine becomes chloride, and gains electrons. This reduction is the gain. This is reduction. Now the last point to make here, yeah, just to show you that half equation, the chlorine is becoming chloride. Chloride. Balance for atoms, balance for charge. Notice the electrons are on the opposite side. Whenever you do redox, they should always be on opposite sides because it tells you that one the opposite of the other. Yeah, it's like a white flag as to whether or not you should continue. So that one's good. And now we need to say why it's redox. Both occur at this, both reactions happening at the same time. So, redox. I like it. Moving on. Next. Chlorine reacts with hydrogen from hydrochloric acid. Write a chemical equation for this. Chlorine, it ends in -ene, which tells me it's diatomic. Yeah, this is going to be diatomic. The next one is gen, ends in gen, so it's going to be diatomic. So Cl2 plus H2, and then you have to say what's hydrochloric acid. Well, hydrogen forms +1, chloride forms 1-, so it's going to be HCl, and don't forget to balance. Now, if you want state symbols, chlorine's a gas, hydrogen's a gas, and actually I'm mentioning this for a reason. HCl makes an appearance quite often at iGCSE at edexcel, and you do actually need to know that hydrogen chloride is a gas. It is not hydrochloric acid. So that there, this compound here, is hydrogen chloride. Yeah, it is not hydrochloric acid. HCl aqueous is hydrochloric acid. Be careful. Yeah, it's just nice to mention it. Comes up in diffusion a lot. Okay, some methyl benzene is poured into beaker A, some water poured into beaker 2, or beaker B. Hydrogen chloride gas is dissolved in each liquid. A separate piece of dry blue litmus paper is dipped into each solution. Explain what happens to the litmus paper in each one. Right. It's interesting that I just mentioned that in terms of hydrochloric acid. So the hydrogen chloride now dissolved in water is going to become hydrochloric acid. That now becomes HCl aqueous. It now ionizes in the water. Yeah, there we go. And this is what makes something acidic. What that means is, so for beaker, but in beaker A, they've not dissolved it in water. And you're taught at GCSE in acid-base theory that an acid is not an acid unless it's in water. This fact is so important And this is not dissolved in water. It's dissolved in a completely different solvent. What that means is this is not going to be acidic. So first thing to say is that the litmus paper will remain blue. Brackets, no change. Yeah. The next thing is we need to explain why. The HCl molecules will not ionize or dissociate, whichever one you prefer, will not ionize, stroke, I like to put both, dissociate in methylbenzene. Now, students are out there saying, do you know what, hang on a minute, how am I meant to know that? Well, guys, I hate to say it, you're not meant to know that. What you're meant to realize is why would they be asking it if it did? And it's tricky that. What you just need to remember, guys, is it needs to be in water. Just remember that. It's just a good rule to have in your head. So the HCl molecules will not ionize or dissociate in methylbenzene, so no H pluses to make it acidic. I like it. H plus is what makes an acid an acid. Next, beaker 2. Oh, well, now beaker 2, of course, is in water. So litmus paper will turn red. Got to know your indicators. Yeah, and the reason being is HCl molecules ionize in water, producing, it's quite repetitive this, producing H plus ions, so it is acidic. Cool, moving on. It's quite a repetitive answer. I didn't understand that question. Do you need me to explain it again, Mita? I'm quite happy to if you'd like me to. So what you learn is, so very early on in year 7 chemistry, you learn acid-base theory very basically in year 7. You learn the pH scale. Now, one of the things that, yeah, no problem at all. So you learn the pH scale, and Mita, I wonder if you ever asked why the H was a capital. The reason being is pH stands for the potential for hydrogen ions. It's the element hydrogen. The reason being is H plus is what makes an acid an acid. So you learn about pH, and then you learn the scales, and you see some indicators, and then you get to year 11. And in year 11, what you learn is that when you have acids, let's look at our 4 main acids from GCSE, 4 main acids. HCl, HNO3, good old nitric acid, often forgotten, sulfuric acid, and ethanoic acid. And what we discovered is when you add these covalent, I'm going to actually draw out HCl. When you add these chemicals to water, something really weird happens. You add this molecule to water, and what happens is they break apart, they ionize, they split apart. Hi, Con, nice to see you, dude. So the H plus and Cl minus, the hydrochloric acid molecule now splits apart. And this here, this ion, is what makes an acid. H plus is acid. So if you're wondering what an alkali is, which is a common question at this stage, so lots of students go, hang on a minute, if H plus is acid, then what's an alkali? That's really easy. You know it. It's already there. So sodium hydroxide. You add that to water and it ionizes. And I get Na plus and OH minus. And that is your alkali. And what you realize is that if you have H plus acid, and you add it to OH minus alkali, then what you make is water. The ionic equation for neutralization. That's what this is called. the ionic equation of neutralization explains why water appears, in 95% of the reactions. So that there's neutralization. The acid is H plus and the alkali is OH minus. Now, just to point out, at this point, students really don't like this concept very much. They're like, hang on a minute, prove it. How can you prove that that the acid is actually breaking up? You can actually do it. You can actually do it by showing it via electrolysis. If you take a beaker and you add concentrated sulfuric acid. Now, just to point out, by the way, concentrated sulfuric acid has no water in it, which means it is not ionized. It literally is that in a beaker. And if you then add in some electrodes with a battery and a light bulb, like this, what you realize is it doesn't conduct electricity. It's covalent in nature. There are no ions to carry that charge. This is electrolysis, by the way, from year 10. This is really important. It's hard, this. Understanding that when something's ionic, when there are ions present, it can conduct electricity because the ions can carry the charge. But then what happens is, if you then take that same setup and you add in water, if we now add H2O to this, all of a sudden, the light bulb comes on. The light bulb suddenly lights up. And the reason why is because as soon as you add water, the ions break off and you form these guys. And all of a sudden it can now conduct electricity. So it proves without any question that when an acid is placed into water, it is breaking apart into its ions. And I could actually ask Con this. Con, I really hope you're still there watching. Con, I'd love for you, I don't know whether you're watching the video from the beginning or whether you've picked it up here, but I would love to know whether or not you could tell me what product am I going to get at the negative electrode. That would be very cool. So anyway, so you can actually prove that they're ionizing. So what we now, when they go to this question here, what they're testing here is your understanding that it actually is, in order for the process of breaking apart to happen, it needs to be water. And they've given you here, this here, methyl benzene, is just another solvent. It's just another colorless liquid. And I think that was part of the problem with this question, is that lots of people didn't, I'm here, Con, if I electrolyze dilute sulfuric acid, what am I going to get at the negative electrode? And I wonder if you can even remember what I'm going to get at the positive one as well. It's a bit more tricky, the positive one. But the negative one you should be able to get for sure. And this was a tricky question, Mita, because most students have never even heard. Well done, Con. Hydrogen at the negative electrode. Well done. So just to explain what Con's just done here, he's recognized that this is the negative electrode over here. This is neg. And what happens is the hydrogen ions go over to here and they gain their electron. So if you zoom in on that section right there, what you're actually seeing is here's the electrode and the hydrogen ions float in together. And when they hit there, they gain back their electron. And those hydrogen atoms will gain their electron and then immediately link together. These immediately link together to form hydrogen gas. It's cool, that. TA. So they gain their electrons, and then at the other one, so that's happening at the negative electrode because they attract the positive ion. At the other side, it's a bit more complicated, and you do need to know this for edexcel, by the way. For dilute sulfuric acid, it's not the sulfate ion that does it. At the negative electrode, the positive electrode, it's actually the OH minus ion that actually goes to the electrode, and it loses its electron and becomes oxygen. I know this is actually an edexcel speciality. I know it becomes that, and then I have to add water over to there, and then I think I need 4 of them, and then I need 4 electrons, I believe. You have to actually know that once. Does that add up? Not quite. If I double that, it does. There we go. Yeah, that's what's, this one's happening at the positive electrode. Positive electrode. And that one's happening at the negative one. Anyway, so going back to this. So Mito, it's not your fault. It was just the fact that most students didn't even know that methylbenzene was a liquid. And it freaked them out. But what you needed to realize was that they're doing something very deliberate here. They're wanting to see that you understand what is happening to an acid when it goes into water, and it is ionizing. Just to show you the others. So just to show you all the other equations for these. So add water, add H2O, H plus, Cl minus. Right, add water, H plus NO3 minus. Add water, 2 H pluses, plus SO42 minus, twice as strong acid. What is methylbenzene? It is a colorless liquid. That's what it is, commonly known as toluene, if you're interested. Yeah, it's just an organic, it's an organic liquid. It looks like this. This is methylbenzene. This is benzene itself, and then it has a methyl branch at the top of it. I'll get rid of that, there you go. There's methylbenzene, and it's a colorless liquid. Yeah, I know, and it was a nightmare, and it was tough for students that. Okay, I'm gonna, Mita, has that helped at all? Am I okay to move on to the next one? Are you okay with that? I hope that helps. I need to do some, yes, please, okay. Okay, so next, the table shows information about the effects of adding sodium hydroxide to solutions containing zinc, calcium, and aluminium. So a student is provided with a sample of white solid. The student dissolves some of the white solid in the water. Con will literally be, Con will be looking at this going, we are literally doing this right now. A student is provided with a sample of white solid. The student dissolves some of the white solid in water and then adds a few drops of sodium hydroxide. A white precipitate forms. She concludes the sample contains calcium ions. Explain whether the student's conclusion is valid. Well, no. The answer is definitely not. It could be calcium, but it also could not be. First bullet point. It could be calcium. It could be calcium, but, and there is a big but here, guys, but zinc 2 plus and aluminium 3 plus also give white precipitates. Give white precipitates with a few drops. I don't want to say it. Also give white precipitates. Now that's interesting, isn't it? Explain whether or not the student's conclusion is valid. It could be calcium, but zinc also, I'm going to say, because she concludes the sample contains, it's not valid. It's not valid. Yeah, she's not valid because it could be other things. And we just have to make a decision there, whether or not we agree. And I've put, it could be calcium, but zinc 2 plus also influence, it's not valid. Yeah, it's not valid for her to state that if it can be other things as well. Give a different test to show that the white solid contains calcium ions. Con now knows this. It's brilliant. Test. Flame test. You're going to flame test it, and the results will be an orange-red flame. I really love that. Con, you have literally dropped in, literally at a perfect moment there, Con, into chemical tests. By the way, definitely want to see that mark scheme. I like it. Let's keep going. A hydrated salt. Oh, we're going into calculations. I've got my calculator on standby. Amazing. So a hydrated salt has the formula AB2X H2O. A is a positive ion and B is a negative ion. When a hydrated salt is heated, the reaction occurs. Okay. The scientists heat the sample of the hydrated salt until all the water has been lost. She records the mass before and after. Describe how the students could make sure that all the water has been lost. Right. You are going to heat until constant mass. Full stop. Let's give some details. Heat heat and weigh after, weigh before, heat and weigh after heating. If mass drops, heat again, and reweigh, repeat until mass doesn't change after heating. I hope that makes sense. It is heat, weigh until it stops. Yeah, so if we just do heat, we can even do time. Heat time, yeah, and then mass in grams and minutes. Yeah, and I go heat for 2 minutes, mass 10 grams. Heat for another 2 minutes, mass 8 grams. Heat for 2 minutes, mass 7.2 grams. Heat for 2 minutes, 7.2 grams. Heat for 2 minutes, 7.2. I've got constant mass. Heat till constant mass. Are we assuming no splitting? Well, you're assuming for this, aren't you, Winkit? Yeah. You're assuming no decomposition. Yeah. Okay, next. Use the student's results to find a value of X. Okay. So we've got two things. So if you notice, we have got the mass of the hydrated salt. So I'm going to shrink my pen here, guys. And I'm going to color code it too. This is the mass of the hydrated salt. So that there is 6.1 gram. And then it says mass of salt after heating. That's this guy, 5.2. Right, so we can now work out the mass of water. So we're now going to do step number 1, 6.1 grams minus 5.2 grams equals. Is that the right numbers? Yeah. So on my calculator, I never do any calculation in my head. Why would I ever do that? I'm going to get 0.9 grams of water, of H2O. I like it. Next. So now, split this in half. This is a water of crystallization. So I now have AB2 and H2O. And I now have H2O at 0.9 grams. And this was my mass, if I go back to my equation. That is the mass of AB2. So that's, sorry, laptop's just taking all of the time there. So that's 5.2 grams. What they've now done is given me the MRs. So I can now work out moles. So I've got grams, get to moles. Remember, moles counts particles. Divided by 208, divided by 18. Right, so 5.2 divided by 208, and I get 0.025, and then I get 0.9 divided by 18 equals 0.05. Perfect. Who's bigger? The water one, and it is exactly double it. If I now divide them all by the smallest, yeah, I get 2. So there are 2x equals 2. There are 2 waters. There are twice as many moles. Look at that moles. It's twice the size of that guy. Yeah? So there are twice as many moles of X as there is AB. And yes, Winkit, God, yeah, we're assuming there's going to be no thermal decomposition of the AB. God, yes. Oh, come on. This is GCSE, Winkit. Be nice. So X is equal to 2. Perfect. Winner. I'll take it. Next, describe how the scientist could use a solution of salt to find out if the negative ions are chloride ions. Ah. Oh, should I just get something happening on my chat or something? Okay, no, it's fine. I've just done this with Con, quite literally last lesson with them. So it says, describe how scientists could use a solution of the salt. So, Con, it's really nice to mention, they've already put the sample into water for us to find out if the negative ions are chloride. Right, so add nitric acid to, I don't like it being in red. Add add nitric acid to the salt solution. This removes carbonate ions. Removing carbonate ions. That's what it does. Carbonate ions. I thought you'd done organic with us. I've done a bit con, but not a lot. Not a lot. Add nitric acid to the salt solution, removing carbonate ions. Now we're going to add 3 drops, or a few drops, either one, 3 drops of silver nitrate. Silver nitrate solution. Silver nitrate solution. A white precipitate. A white precipitate will appear if chloride ions are present. Hey, test for the halide ions. It's a winner. Good job. Just to point out, by the way, edexcel is the one that doesn't do this. I'm just going to add the extension for those people doing A-level in the room. This is WingKit. WingKit, that's not enough for you. Well done, WingKit. It's not a mark for GCSE, but it is a mark for AS and A2. So this is now A-level, so Mita, you can ignore me. Confirm the chloride, yeah, add dilute ammonia solution, and the chloride ion, add dilute ammonia solution, white precipitate will vanish, redissolves. I like it. Next. I've got lots of messages coming through, and I really just, I want to ignore them, but I'm worried in case someone's saying to me like, no, it's fine, it's okay. Next, the test shows that negative ions are chloride ions. Okay, calculate the relative atomic mass of metal A in the anhydrous salt. Okay, that seems reasonable. So what that now means is they gave us the MR of the salt. It was 208. So AB2 was 208. There we go. So AB2 equals 208. And they've now just told us it contains chloride ions. That's perfect. A chlorine atom weighs 35.5. And a chloride ion has gained an electron which are negligible. It's still 35.5. And therefore there's 2 of them in it. So I'm going to do 35.5 times 2 is 71. Right, now what we need to do is minus 71 from that. 208 minus 71 gives me the 137. And it's going to probably be in group 2. Yeah, so relative, oh, by the way, that's it. The relative atomic mass is 130, well, yeah, it's 137. Identify metal A, where's my periodic table? 137, I have barium. Winner! Nailed it. I always love it when things come together. Barium. Identify metal A. Winner, thank you. Next. Submetals can be obtained by heating their oxides and with carbon. Give the name of iron ore. It is hematite. Just got to know that, folks. Hematite. Explain the role of the hot air in the blast furnace. Now, Mita, just to let you know that you're doing the new specification. Even if you're in year 11, you're still sitting the new spec. The blast furnace has actually now been removed, which is really nice. You don't need to know any details about the blast furnace. The chemistry is still good. I still teach it, really. So the hot air in the blast furnace, the raw materials that go in are coke, which is carbon, coke in the form of carbon. We also add iron ore, hematite, yeah, and we also add limestone, yeah. So the limestone removes sand impurities. The iron ore is the source of iron, and the carbon is the reducing agent. But here's the thing: the role of the hot air in the blast furnace. So number 1 is to raise temperature. It's hot, yeah. Raise temperature. Raise temperature. Number 2 is to provide oxygen for the coke to burn, producing heat, and the reducing agent of carbon monoxide. Reducing agent. If anybody's wondering what those equations are, I can show you. So we add coke, which is carbon, a purified form of coal, by the way. You take coal. Coal's very dirty. It's full of sulfur. You bake it in an oven, and the sulfur gets evaporated. So you take carbon and you put in a hot air from the blast furnace. This is your air, your hot air, yeah, and it forms carbon dioxide, and that now raises the temperature up to about 1,000 degrees. But we need more temperature than that, so we pump in more and more air. And what happens is the carbon dioxide reacts with more carbon, and it turns into carbon monoxide. And that actually raises the temperature. That's exothermic, and that raises it up to about 1,800 degrees Celsius. And it also makes the reducing agent. That there is the reducing agent for the metal. Produces, yeah. But no details of the blast furnace is now really needed. Oh, balance the equation. Always nice. 2 ions. 3 oxygens. Oh, common denominator, 6. So I need to do 3 and 2. Right, my ions have changed. 4. Yeah, 4 ions. 6 oxygens. 3 carbons. We're done. There we go. And then in this case, the carbon's acting as in that particular equation, the carbon's the reducing agent. Yeah, it's redox because this is being oxidized because it's gaining oxygen. This one here is being reduced because it's losing oxygen. And this is therefore the reducing agent, the thing that's doing the reducing. Next, limestone is one of the raw materials added to the blast furnace. Explain how limestone removes silicon impurities. You may use an equation to help. So number 1, silicon dioxide, which is sand, by the way. Not sand, but sand. And sand, silicon dioxide, is acidic. It's a metal oxide. So it's actually it's a non-metal oxide. So it's acidic. And limestone, calcium carbonate, is a base. Is a base. And so will react. Whoa. No, sorry. So will react with SiO2. Here's the equation. CaCO3. Here was it? Forms calcium silicate and CO2. There we go. Just to actually let you know, by the way, that that's actually not the real reaction. If you actually want the real reaction, the limestone goes through thermal decomposition to form calcium oxide and CO2. And then the calcium oxide is actually the one that reacts with the silicon dioxide to form calcium silicate. But then you can combine those equations to get the same one anyway. So you can actually write down the combined equation, but it's going through thermal decomposition first. There's the thermal is the equation needed? So I haven't quite finished. The answer is no. It says you may use it. You could say 1 mark for saying that that's acidic, 1 mark for saying this is a base, and then the last mark is for saying calciums will react with SiO2 to form calcium silicate. You could write down that name if you prefer. To form calcium silicate, which is a liquid at this temperature. So it pulls out of the machine. How do I want to say that? It's a liquid at this temperature. So it's also less dense than the iron as well. So it floats on top of the iron. It's up here. So out comes at the bottom. Here is your molten iron. This layer here is calcium silicate. otherwise known as slag. I know the common name for calcium silicate is slag, and it literally pours out as a liquid. It's called slag because it's a horrible connotation because it's actually where the insult comes from, because it actually means, in Old English, it means unuseful. They used to just bury it until now, of course, they use it for road surfaces. It looks like a black glass. You see it every day when you walk over a tarmac road. The little black lumpy bits that look like stones is actually calcium silicate. They're sold for use in road surfaces. So it forms calcium silicate, which is a liquid at this temperature, so runs out. It doesn't block it out, it leaves. It also floats on top of the iron. It doesn't mix with it either. It'll be interesting to see whether or not I get that third mark. I could add a whole load of extra things as well. I could be like, oh, it floats on top, but I don't really want to. It's too much waffling. State why aluminium cannot be produced by heating its oxide with carbon. Aluminium, got to know your reactivity series, is above carbon in reactivity. So cannot be reduced by carbon. I'm pretty sure if you just say aluminium is above carbon in reactivity, you'll get that mark. Pretty sure that's all you need. Describe how aluminium is extracted from purified aluminium oxide. Right. Now this one I believe you do need to know a little bit about, although I don't think edexcel are going to be asking you for the details anymore. So number one, aluminium oxide, is put through electrolysis. I believe that's going to be 1 mark. Now you need to give it some details on this. So what we now need to do is we need to describe what's going to happen. So the first thing is we'll need to make it molten. So first, aluminium oxide is heated until it melts. It melts, 1 mark. Whoa, heated until it melts, 1 mark. Just plug my laptop in. I think it's on now. Yeah, cool. Heated until it melts, and then they add cryolite. That will be a mark all on its own. Molten, cryolite, electrolysis, these keywords are hitting everything. So then they add cryolite. Now, just to let you know, that cryolite reduces the melting point. That's all you need to know about it. Reduces melting point. What was it? Oh. Reduces melting point. What they now do is they now run electricity. They now use graphite electrodes. Apply electricity. Could have done the whole thing from a diagram, I'm going to draw the diagram as well in a second. It's going to be interesting to see how many marks I get. Graphite electrodes apply electricity to split aluminium oxide into aluminium and oxygen. Now the last bullet point, oxygen reacts at this temperature, at this temp, with graphite electrodes running out of space. Electrodes need to be replaced. Electrodes need replacing so often. Every so often. So that'll be a very interesting question to mark. The picture that I literally have in my head is this one. If I'd drawn this, I reckon I would have got all the marks. Yeah? labeled that there as graphite. That's there as graphite. This is molten aluminium oxide and cryolite. When the electrolysis happens, the aluminium comes out as a liquid down here. Oxygen gas is forming up here. I can give you the half equations. The aluminium 3+ gains 3 electrons to become aluminium. Oxide, balance it with those +4 electrons. That one's going to lose 2 electrons. So this one's going to be, this is gaining. And so oil rig, oxidation is lost. This is lost. So that's oxidation. This is red, reduction. Yeah, and it becomes oxygen gas. But then the oxygen gas reacts with the graphite to form CO2. If I'd written all of that down, I'm pretty sure they probably would have given me all the marks hilariously. But that's going to be a really interesting question, because that's not nice, that. It's just having you guys having to basically like spit out bullet point facts. Not very nice. I understand why you didn't like it. A student does a titration to find the concentration of solution of aqueous ammonia. Used to pipette 25 centimeter sample. Okay, let's go to the question. State what the student should do while adding the acid to make sure that the indicated color is changes color permanently. Swirl. You swirl it. Yeah, that's the whole point of the conical flask. The whole point of this piece of equipment is so you can swirl without spillage. Yeah, you're adding in you're titrating, you're adding in your acid drop by drop, and you're going to be swirling it whilst you're doing it. Swirl conical while adding. Swirl conical whilst adding. I bet, or whilst adding. Yeah. Next, okay, so concordant results. Right, concordant is within 0.2 at GCSE. So you go 3 point, that's too far apart. Nope, that's not 0.2. Oh, that's 0.2. Yes and yes. Yes, yes, and yes. One right in the middle. I like it. 3 concordant results. These guys here are within 0.2. You can do the maths if you like. So on my calculator, I'm doing 23.15 minus 22.95, and I believe it's 0.2. Winner. So that is definitely concordant. And then these guys, yeah, are also 22.95 minus 23.1. It's 0.15, so that one's also in concordant as well. So those 3 are in concordant. Concordance just means within 0.2. Next, use the concordant results to calculate the average. Okay, 23.15 plus 22.95 plus 23.1, all at 0.10. Don't forget, all divided by 3. Very reasonable. 23.15 plus 22.95 plus 23.10 equals 69.2 divided by 3, and I get an answer of 23.0607. There we go. Winner. I like it. Technically, I think that you can't really... oh, actually, no, I'm okay with that. That's what the average says. That's what I'm putting. Should be to 2 decimal places. Fine. Let's go to the next one. Right. So, okay. Calculate the amount in moles in sulfuric acid. 20. So we've got sulfuric acid's volume, and they've given us it again. But then we need its concentration, which is here. So number of moles equals concentration times by volume over 1,000. It's over 1,000 because I'm in centimeters cubed. Right, running my numbers. Number of moles is concentration, so easy. 0.08 multiplied by the volume of 22.70 all over 1,000. And I get my answer. 0.08, check my calculator carefully, times 22.70 all divided by 1,000. There we go. My answer is 1.816 times 10 to the minus 3. So I will then put that 1.83 sig fig 2 times 10 to the minus 3. There you go. Done. Calculate the moles of ammonia in the solution. Right. Well, the ammonia solution, the volume of the sulfuric acid was 22.7. The volume of the ammonia was 25. You can see that up there. Now we need the concentration. Well, the concentration of sulfuric acid was 0.08, but we don't know the concentration of the ammonia. But what we do know is that the ratio in the equation is a 1:2. What that means is the moles of sulfuric acid, which we've just calculated, which I'll write down in red as 1.82 times 10 to the minus 3, to get to ammonia, I just double it, because to go from 1 to 2 in the equation, I'm just going to multiply it by the mole ratio. So 1.82 times 10 to the minus 3 multiplied by 2, because the ratio of sulfuric acid to ammonia was I'm just going to go, I'll do this, sulfuric acid, ammonia, a ratio was 1:2. So we're going to double it, number of moles. I've got that number on my calculator, by the way, 1.816 times 10 to the minus 3, times by 2, and I get 3.632 times 10 to the minus 3, and I now put that number down there to 3 sig fig, 3.63 times 10 to the minus 3 moles, and I'm done. Next, calculate the concentration of ammonia. Well, now I've got its moles. Number of moles equals C times V over 1,000. Reorganize for concentration. Bring the 1,000 over, moles times 1,000, and then bring the V down. So over V will give me C. Right, so my number of moles is 3.63 times 10 to the minus 3 times 1,000 and over the volume. And the volume was up here in the table at 25. Yeah, so I just now reorganize that, put the 25 into there. So still got the number on my calculator, times 1,000 divided by 25, and I have a concentration of 0.14528 moles per dm cubed. And on my final answer, I'm going to write it to 3 sig fig 0.145, and I'm done. Next, describe how you could use the method of crystallization to obtain a pure dry sample of ammonium sulfate and from a solution of ammonium sulfate. So they've already given us the solution here, guys, which is quite nice. So the first thing is I've got a beaker containing a solution of ammonium sulfate. Oh, we can even work that out. Ammonium sulfate, aqueous. I like it. So what I now need to do is I need to obtain pure dry crystals. Right? They don't ask for hydrated crystals, so we make an assumption that this is therefore going to be anhydrous. They just don't care. So what I'm going to do is I'm going to first of all transfer solution to evaporating basin, evaporating dish or basin, whichever one you prefer. Right, so what does that look like? Transfer that into an evaporating basin. There's my, oh, it's going to be on a pipe clay triangle, isn't it? It's going to be on a pipe clay triangle. Yeah, and now I'm going to heat it. Yeah, now I'm going to heat until let me make that clearer. Heat until approximately 80% of water is gone. Next, so what that now looks like is I've now got a small amount of liquid left. Yeah, only about 20%. Yeah, now what I'm going to do is I'm going to test this with a glass rod. Yeah, use glass rod to see if crystals form. This is, by the way, this is simply to do with saturation. The solution now is massively saturated. Yeah, I'm now touching it with this cold glass rod. The temperature suddenly makes the liquid lower, so the solubility drops and the crystals appear on the glass rod. So use glass rod to see if crystals form. Right now, leave to cool down. Leave to cool down so crystals form. So I just leave this to cool down now. And what will happen is you will now have crystals forming in the solution as it cools, as this cools down. The solubility drops, so the crystals reappear. Right, now I need to do is I need to filter them out. Now filter out crystals. Filter out crystals. Wash, now these crystals are soluble in water, so I'm going to wash with alcohol, or wash with, now filter out crystals, wash crystals with, I like washing them with propanone or ethanol, either one. Let's go with acetone. You probably don't even need that sentence. Wash with, it does say pure though, so they need to be washed. Wash crystals with acetone, and then leave to dry, and you're done. Be interesting to see how many marks I get for that. So we've evaporated out most of the water, checked with a glass rod to see if crystals are formed. We're checking for saturation at that point. Now we leave it to cool down, the crystals will form. Then we filter out the crystals, wash the crystals with acetone, and leave to dry. We're done. Oh, and that's the end of the paper, which is nice. So now, guys, just like I did last time, let's now mark it. It's very reasonable, so it's always good to check. So this is where we got up to last time. I've no idea how long this has been going on for. Haven't got a clue. Documents, exam papers, GCSE, mark scheme. No, let's have a look. Can't we wash the crystals with distilled water? Yeah, can you put it in a drying oven? Yeah, that would probably be okay, Con, to put it in a drying oven, because they don't care the fact that they're hydrated or not. If you wash them, okay, Nita, I think it'll be fine to, like, edexcel, they're idiots. And the reason why I have a problem with what you're saying there is because these crystals are soluble. Imagine we've got a whole load of salt crystals in our hands and we wash them with water. What's going to happen to our salt crystals? They're just going to dissolve in the water and wash down the sink. You don't want to wash them in water. You'd want to wash them in a solvent that it's not soluble in. So I like to choose, I don't think they'll care. Right, so what question, this is question 7. There's 6, 7, okay. Right, so increasing, the greater the relative atomic mass, the higher the boiling point. Does not, okay, yeah, I like it. 1 mark. There. So yes, as you increase, as AR increases, boiling point increases. I like it. They do, look at that, isn't that, allow full outer shell stroke energy level. Do not easily gain or lose electrons. So they're actually doing the yellow one as the primary. Yeah, but we got both there for sure. Next, an element in group 7. Okay, so all have 7, same number of electrons in outer shell of electrons. Allow all need to gain 1 electron to have full. We've definitely got that one. I like it. Next, a nice easy equation. No state symbols when needed. Nice easy equation. Orange was like allow, brown, yellow, any combination. Next, no reaction as bromine is less reactive than bromine, so bromine cannot displace. Ooh, no reaction will take place as bromine is less reactive. Bromine cannot remove the electrons from chloride ions. Ooh, mine's better than theirs. That's answer that bromine cannot displace chlorine. Technically mine, but mine is not on the mark. I won't give myself it. Mine is better. That's where edexcel would have to have a conversation because mine's better. It is actually better, Kevin. Mr. Duncan, I have to go. See you Monday. No problem at all, Winkit. Take care. Have a nice weekend. I will add to this though. I won't give myself it, even though my answer is good. I'm actually going to put therefore cannot displace. I'm going to add that to my notes. Yeah, because I need to make those improvements too. So cannot displace. It's nice for me to add that in. Next, explain why it's a redox. Iodine ions lose electrons, so oxidize. Yeah. And then chloride ions gain, so reduction. I like it. Both happening at the same time. Or we're happy. I like it. Next, equation. HCl unbalanced, love it. Litmus stays blue. Litmus will remain blue. HCl chlorides does not ionize. I like it. Next one, it turns red because they form H plus ions. I like it. Next. Not making a valid conclusion because it's also, I like it. There we go. Because not seeing other excess tests, yada, yada, except, yeah, that's fine. It is not valid because it could also be those guys. I like it. Flame test. Orange red. Tick. They actually got brick red now. Wow. Edexcel finally wising up. Next. Right. So heat and then heat again. Heat and reweigh until constant mass. Heat, reweigh until constant mass. I've done mine the other way round. Yeah, but it's nice to do so. X equals 2. So look at the marks. M1, 0.9 grams. Tick. M2, yeah, doing the divisions. See the divisions? Yeah, I don't know if you can see what I'm doing there. The 2 division steps here are M2, and then dividing the bigger number by the smaller number, yeah, it gives us our 2. Yeah, so we're happy with that. Ugh. They actually wanted the 1:2 ratio. They don't actually. It's the numbers are there. That there was the actual number. So just to show you where the marks come from. Shouldn't circle those. So that one's a mark. That one's a mark. Yeah, I like it. Next, add nitric acid, add silver nitrate, and then white precipitate forms. I like it. Next, 137 and barium. Like it. Hematite. So these are the questions which I thought were interesting. Hematite raises to provide oxygen for the coke to burn. Oh, I like it. So provide oxygen for the coke to burn, producing heat in the reducing agent. That's absolutely fine. React with M1 provides oxygen. M2 to burn coke. I like it. There's coke carbon. Nice. Next, balanced equation. Thank you. Next. Well, this was the interesting one. So limestone decompose. Oh, they wanted all of it. Limestone decomposes to form calcium oxide. Calcium oxide reacts with silicon dioxide to form molten slag. M3. How fascinating. So actually, I needed all my equations. That's brilliant. They actually wanted these ones. Decomposes, reacts with it to form molten slag. So what did I put? Sand is acidic. Calcium is a base and will react with it, given an equation, to form calcium silicate, which is a liquid at this temperature, so it runs out. So at least I'd get M3 for that. But really interesting. So they wanted more than this. Oh no, hang on. Yeah, scores M3. Yeah, okay. So they wanted the equations. I gave the equations as an extra thing on the other side, but I have to say I'm a bit disappointed by that. Because I don't think they should be massively concerned about whether or not it's the calcium Anyway, not that it really matters. We know for now. I think I'd probably get stung for that. Anyway, next, these ones were much more difficult. So aluminium is more reactive than carbon. Done. Aluminium, or say 4 marks. Aluminium extracted via electrolysis. Done. Aluminium mixed and added with cryolite. Done. It must be done molten. Electrolysis molten. Carbon graphite and anodes used. Graphite electrodes. Aluminium ions discharged, forming at the electrode, except equations. I'd have definitely got 4 for that one. Yeah, reasonable. Swirl. Next, I like it. And the calculation itself. There we go. Except correct answer without working 2 marks. Wow, they actually wanted the 4 sig fig. Do not penalize them with training zeros. Interesting. They wanted it to 4 significant figures. That's really strange. I mean, I gave it, but I don't see what the issue would be there. For 1 mark. Oh, interesting. Anyway, M2. Okay, yeah, so double it. Yeah, I like it. Times by 2. And then 145, 0.145. Really weird that they're wanting so many significant, except any number of significant figures except for 1. Okay, fine. Don't like doing that one. There you go, that one's correct. Next, salt solution, I think was the final one. So, this is really interesting. I love these ones. So, 4 marks. Boil the water until crystals form in the sample solution has been removed or cooled. Except heat to boil to produce a saturated solution. Except heat boil until crystals start to form. Heat boil till crystallization point. Allow heat boil to evaporate some of the water. Okay, so I definitely get transverse and the heat until 80% of the water is gone. I'll get that. M2, cool, leave them for crystals to form. So they've ignored the glass rod bit. Fine. So leave until to cool down. Now leave to cool down so crystals form, and then filter out the crystals, and then suitable method of drying crystals. Yeah, place in warm place, leave in, but leave to dry. Use filter paper. I need a method. Leave to dry. No, it's not enough. Leave to dry in warm place. I need to add that, or just use paper towel. Use paper towel to dry. And that brings us to the end of this session. What fun. It's been an awful lot of fun, folks. I've really enjoyed this. It's actually been quite good paper. I've enjoyed it. I'm trying to find out where my other, there we go, StreamYard. There we go. Right, Meter, I really hope it's been useful for you. When you want your next paper being done, when you choose the next one, let me know and I'll do it with you. So I hope you find this useful, guys. Have a great weekend. It's the end of Friday, of course, so have a great weekend, everybody, and I'll see you all soon. See you later.